Alright, hell yeah. So we have linear algebra, and I'm going to derive the Grant. I call it Grant, it's Gram. And I need to look this guy up, you know what I mean? Get a name, get a face to a name, you know what I mean? So hell yeah, so we're going to do the derivation. In the other video we did the derivation of kind of the first go around. And booyah. And there's no expectations for this video. We're going to learn about the dot product. We're even going to learn that that symbol is the dot product. That's the hardest thing, I think, coming from just kind of like a classic background of not using matrix symbols and matrix algebra. Yeah, and then using this and then kind of seeing what's up. But I think we can explain that. So hell yeah. So this is the linear algebra book that we're working out of. I'm just going to throw this up for a couple seconds. Hell yeah, but we're just going to do it from scratch. And I guess we have to even figure out what even we're doing. And so, yeah, and I can't explain everything, but I just know that in matrix algebra, sometimes you'll get, well, let's get a 2D. So we have x, y coordinate. Maybe one of your points is right there, okay? And we're just going to say that's 2, like, you know what I mean? Let's say it's 2, 0. Hell yeah. And then we're going to get a point, we don't have to get too tricky. Let's get a point right there, 1, 1, 1. Okay, so what we have is if these points are a representation of a length and a direction from the origin, then they are a vector. So I can represent this, these 2 points as a vector. And so what we do is we say that we represent it like this, 2, 0. And then this one will be 1, 1. And then just the general vector, we'll just use x. So this is our set of vectors. Now this isn't just one vector, this can be a whole set of vectors, but it's going to have units of, this is going to be the x value, this is going to be the y value. Cool. So, so my set of vectors, and I don't even know if I'm using these terms right, I've just seen them done, you know, I mean, sometimes mathematics is just, some of it I would imagine is just, hey, I'm trying to say something, and I'm going to say something with symbols. But we're going to say that this, maybe, and I don't even think you say it like this, because I think this would be like a set. Like, don't you have to use capital X? And that's what I hate doing videos like this, where it's just like, I don't want to run up to Google, you know what I mean? And so, is this how I would represent it? Like, this is going to be x1, and this is going to be x2. And so we would have x1, x2. And if we had a bunch of them, then you would even kind of write this as like x1, and then dot, 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 x, you know what I mean, n. Yeah, that sucked. See, but no, this is good, because I like to challenge myself, you know what I mean, on stuff like this. Does this symbol only apply to a set, which I'm kind of halfway familiar with, where like you could have you could have a set of numbers, this would be a set of vectors, but anyway, hell yeah. So I can say that this is x1, vector x1, and this is vector x2. Alright, so let's get on to something a lot cooler than what we just did. Alright, so this is what I can relate to statics. Statics might be a sophomore level college course, and even the first chapter of the statics book, you'll have like, you know what I mean, like a tugboat. You know, you'll have a big ship. I'm just going to represent the ship as a chunk of mass, you know what I mean, like that. Maybe you're looking down on it and the ship just looks like a little dot. And then from that little dot you see a rope, and then there's another little dot, and that's a tugboat. You know what I mean? And then so this one is going to be going that way. So, and then this tugboat, usually you can only pull in one direction. And you know what I mean? For your homework, you know what I mean? Determine what directions you can actually go with this. And let's do this, because this will actually make sense. If you can only pull, if this tugboat's right there and this tugboat's right there, and you can only pull this direction with that tugboat and that direction with this tugboat. What are the locations that this could actually go? And we know that these are forces. You know, maybe this is force 2, this is force 1. And even, you know what I mean, and just the fact that we know, like, oh, those tugboats are putting a force, but mainly we know that those tugboats are actually just moving the ship. But then we also know that those tugboats are applying a force. And I think that's one of kind of the simplest and coolest relationships, that we all know physics from the fact that we know that things can go from here to there. And we know, you know what I mean, it took some sort of, that's supposed to be a bicep. You know what I mean, some sort of oomph to do that. Alright, hell yeah. And, cool. And so in this thing, we're going to say that, well, let me just spell it out. So we can go this way with that force. And let's say this tugboat just turns off. You know what I mean? It can turn on, but it can't go the other direction. So this is just a rope. If the rope goes slack, you can't push. So that's going to be the first thing we come across. So hell yeah. So the tugboat could go that way. Hell yeah. And then can the tugboat go this way? Hell yeah. So we're going to turn that one off and this one on. And now the tugboat can go that way. Now, if you turn them both on, we're going to, you know, we add vectors by going this and then that. So I could get to there pretty easily. You know what I mean? So there, if both of these tugboats are, you know, kind of the same, they're putting out the same force, we can actually just look at these distances. Well, if this rope is like 100 whatevers, 100 meters, and that rope's 100 meters, then this tugboat is putting a force of whatever, and this is going to be the same, then I can represent the vector of that force to be exactly the same length. You know, if I'm representing this arrow to as 100 meters long, but I'm saying it's not 100 meters, it actually has units of, and let's give this 20, yeah, what would be force? Well, let's just say 20 newtons. Hell yeah. And then, so cool, that arrow is 20 newtons. What's this arrow? That arrow is 20 newtons by inspection because they're the same length. Alright, hell yeah. So, now here's a question. Can I get the tugboat over there? You know what I mean? So if all I can do is turn this one off and I go that way, turn this one off and this one on, I go that way, have them both together and I'm right there, let's say, have this one just be like a tenth, so I'm going to go a tenth that way and then the full that way, have this one just be a tenth and then I'm going to go the full that way. So it looks like I can hit any location in between here, but that's it. If this tugboat can only make this angle with the ship and this tugboat this angle, you know, I can vary the forces, but I'm just going right into there. So we're going to, you know, now say that the tugboats, this tugboat has a steel rod. So now we have a steel rod going out to this tugboat and then a steel rod going out to this tugboat. These steel rods can now provide compression. And now, when we have this tugboat, I can either put a force that way or that way. And then what we're going to find, just to spell it out, is this ship can now go anywhere. Just with these two tugboats. So here's tugboat 1 and here's tugboat 2. So let's check it out. Let's try to get to over here. And so what we do is we use the parallelogram method of adding vectors. And because I'm putting a force vector right at this from this tugboat, the force vector is a line of action. And so I can always take that vector and put it right at the midpoint of the ship. You know what I mean? So I could go this way or I could go that way. So those are the two directions I can go from this tugboat. This tugboat, I'll put that arrow here or here. So those are the two directions. Okay, hell yeah. And how we add vectors using the parallelogram method is, well, and even if you're just not familiar with it, what I would first do is just draw a bunch of perpendicular lines. So if this tugboat can only pull that direction, you know what I mean, then draw a bunch of lines that direction. If this tugboat can only pull this direction, draw a bunch of lines this direction. And then, you know what I mean, figure out, hey, does this line go through that point? Hell yeah. And then does one of these lines go through that point? Hell yeah. And so let's even move this out. So what you can do, and then you can get to this point two different ways. Basically, you know what I mean, to get to there, I could, it makes sense maybe to push, I mean, the boat's going to go that direction. That literally is the resultant. So this tugboat has to push that way. So it's going to push that way. And then this tugboat's going to pull that way. And so that's how you're going to get there. Or you could say that this tugboat pulls that way, that much force. And then this tugboat pushes that way, that much force. So this way and that way is the same as this way and that way. And so this creates a parallelogram. And, you know, it's called it's the parallelogram method of adding vectors. You know what I mean? If your vectors, if your two tugboats are like this, I mean, hell, it could be the square method of adding vectors. So if here's your line of action from the tugboats, and then here's your ship in the middle, hell yeah, I can get to there just by turning this one on that way, and then that one on that way. You know what I mean? So this goes positive, and this tugboat goes positive. I could get over here by this tugboat pushing this way, and this tugboat pushing that way. So when the tugboats are perpendicular, you know what I mean, the light goes on and you're like, oh yeah, no duh, I can get anywhere. This tugboat's going to push down, this tugboat's going to push over. But kind of the take home, and it's kind of fascinating even just doing this because, you know, when you do something that seems complex, probably the last thing you're going to do is be like, you know what I mean, like what's the general gist of what we're doing? Well, the general gist, so now I can just say, is that you can have two vectors. These two vectors are what they're going to call is they're going to be linear independent. Linearly independent. Meaning that you can get this tugboat to any location. You know what I mean? And in matrix algebra, you would say if I multiplied this by a scalar c and this by a scalar k, then I can get a resultant. And if I added those together, I could get a resultant anywhere. So if you said the resultant was the addition of these multiplied by scalars, and the scalars could be positive or negative, then I can get anywhere. But wouldn't it be more convenient to actually have this one just be perpendicular? You know what I mean? Because then if I wanted to get to there, I just, you know, walk that way and then walk that way, which we're all used to. We're all used to going perpendicular. And the reason why we're used to it is because, you know what I mean, if your two vectors are like this, we say they interfere. Or if they are perpendicular, they don't interfere. If I walk this way, you had to walk that. If I'm trying to get to there, I had to walk that way. You know what I mean? And if I walk that way, I have to walk that way. You know what I mean? And if you do them simultaneously, sure, you're going to move that direction. But if your vectors are like this, you know, these two ship operators now have to communicate and be like, whoa, like I'm, like, sure, I'm trying to get this thing over there, but then what does this have to do? It's like, well, this operator says, well, go twice as much, and then I'm going to pull pretty decent. Isn't that crazy, just to get that ship going that direction? So that's where these two vectors, sure, you can add them together with the scalars we talked about to get any resultant, and the ship analogy works pretty well. But wouldn't it be convenient just to do a perpendicular? And because this is matrices, or just matrix algebra, what you're going to come across is problems where you don't have x2 and x1. You know what I mean? You're going to have, your next ones are going to be x, y, z. You're going to have three of these. So you're going to have x, y, z, 1, 1, 1, 2, 2, 2, and then x, y, z, you know, threes. And so this is going to be x1, x2, and x3. And then hell yeah. And then so you're going to have 3 vectors in 3D space that are just all over the place. You know what I mean? And then, sure, doesn't the same analogy, if these are 3 tugboats and they're pulling from there and here's our ship, can't we get this ship going anywhere in 3D space? But what a conundrum, you know what I mean? Like, what is this? It would be cool, I mean, if you were just going this direction, and then in the z direction, well, you know what I mean? Cool. Let's get one of these broken down. Let's just go in that direction. The other one go in the other direction. But this is the first caveat of the Gram-Schmidt is that it's not quite like this proof actually doesn't say. All right, hell yeah. So we're back. And yeah. Oh, yeah. So this process, the first vector is what it is. You know what I mean? So if you got 3 vectors going wherever, we're just going to choose this one as our first one and be like, cool, that's going to be, you know what I mean? You could call it X. If you do call that X, hell yeah. Then the other one can be, you know, in the Y direction. Now, I am going to say that I'm sure there's a way to get your vectors to have a right-hand rule. You know, I don't know. That never really came up. But what you're going to get due to this derivation, or what I think you're going to get, is the fact that you're going to get a perpendicular vector, but you're not going to know if that vector is, you know, what direction it's pointing. So if I typically have like an x direction, y direction, and this way, maybe I have this as my first vector, and when I do the calculations, and I'm not going to get this vector, but I'm going to get the opposite. So maybe it would be a left-hand rule. But then when I do the other one, you know, maybe it's, you know, same, like a 50-50 chance. So that seems too heady to actually go through and have a right-hand rule convention. And I don't know in matrix algebra, because the whole deal with matrices is that you might have, you know, you're going to go from 2D space to 3D space to 4D space. And all that means is that if you have 3D space, all those vectors are perpendicular. And then you're going to say the next vector is perpendicular to all 3 of those. We just can't visually draw that, you know, in our 3D space. But basically, the same thing, they don't interfere. So even if you have 4 tugboats in a 4D world, they're all chill since you did this process and got them perpendicular. So this process is getting vectors perpendicular to each other, and cool. And then once you do get the vectors perpendicular, you know what I mean, so then we have these perpendicular vectors. You can, and they're going to have values, whether it's just, ours are just going to be 2D, x, y, just 2 points. Now, is that true? Oh, yeah. But I mean, for ours we can just go to 2D. But if your point started with 3 points, and you had 3, you know, like from this scenario, you could take these vectors and find change their, and it's called changing their bases to where yeah. And I guess that makes sense. Is like you're still saying that these 2 vectors are in the xy plane, either this sheet of paper or just a flat surface. And you know that these vectors can get to any point in this xy plane. Well, cool. If you already know that you have 2 vectors that are linearly independent about the xy plane, then I think we can just get, I think that's the property of it. It's just like, well, we can actually take these 2, we can take this, would you say subset? Anyway, I don't like to use matrix terms because I'm just brand new to it. But anyway, so we can take these 2 vectors and make, and what would you say, that they're equivalent? or I guess you're just saying, hey, we have two vectors that are linearly independent. You know what I mean? And if they weren't linearly independent, we can talk about that. If the two ships, if the two tugboats are pulling on that ship this way, even if they have this bar, steel bar, the only direction they can get this ship to go is back and forth. And that's going to be one-dimensional. So they can only get this ship in the R1 space, so just the one-dimensional space. And then the other, yeah, but yeah, it's fascinating even with vectors. Even if I have a slight angle of the other tugboat, I can still get to any point in R2. So as long as the two vectors aren't parallel, then they are a linearly independent set of vectors where I can multiply them by scalars to get any resultant in that space. But still, wouldn't it be convenient just to represent them as a perpendicular set of vectors? Alright, hell yeah, I think I'm answering my own question. Because, you know what I mean, we get a problem where we're given maybe two tugboats, and this tugboat can pull this much or push that much, and this tugboat can pull this much or push that much. So those vectors, these two vectors still have, like, magnitude. Like, you know what I mean, let's say this is 4 and 4, and this is 2 and 0. You know what I mean? So they still have magnitude. But what we're doing is we're just saying, cool, we know they're linearly independent, and we're trying to find a basis, I think that's what they call it, a basis that's just perpendicular. And then once we have this perpendicular basis, yeah, they're going to be any arbitrary amount. I think it's the fact that the value, the magnitude of the vector is kind of irrelevant. It's just the fact that for solutions, having things linearly independent, yeah, so let's see. Hell yeah. Alright, so I just took a 5-second pause. But what we're showing is that linear independence, you're starting with R2 space, you're starting with a 2D vector plane, you know what I mean? And these vectors can be anywhere in the XY plane. And then what we're ending with is, like if we say like what can these vectors, the scalar addition of these, so if we took these two vectors as a basis and we could multiply them by scalars and then add them, what would be the space? And the space for linearly independent vectors is R2. And that's another way of saying you can get to any point. Cool. If these were not linearly independent and we had both tugboats pulling in the same line, then sure, you could multiply this by a scalar k and this is scalar, you know, c, vice versa. And this could be positive or negative. But the only direction you're traveling is either positive this way or negative that way. And so you're having, and both these vectors still are part of R2. They still have an x and a y component. And so they're still 2D vectors. 2D vectors, is that what you'd say? You know, vectors in the xy plane. But then their scalar addition, is that what you call this, scalar addition? Yields, its range is only in the R1 plane. So I mean, just the fact that you can only move in one direction, that tells you that is one-dimensional. Hell yeah! I think this is the most important part of. I mean, because I can do the Gram-Schmidt. Who cares? You know, I can walk through the process, but you know what I mean. Like I'm struggling here. This is good. You know, what the hell is a linearly independent set of vectors? Well, it's a basis, and if you have a linearly independent set of vectors, even if they're just bizarro values, it's still a basis for that range. So if this is R2, a linearly independent set of vectors can be scalarly added to reach any point in R2. If they're not linearly independent, then And you could drop a range, and if these started at R2, you don't just have to stop at R1. There's a chance that this vector, 0, 0, is in R2. And then check this out, another vector, 0, 0. So this is x1, this is x2, is also in R2. It's a vector with a length of 0, starting from 0. You could put the little arrow on it, and you got two of them. And if you scalarly added these, the only vector you're going to get is another 0 vector. And hell yeah, and I think that's real important for matrix algebra, is always take things back to like the most fundamental you can get. Because that took an R2 that was not linearly independent, that's linearly dependent, and it yielded scalar multiplication. And I don't even know if that's what you would call it, the scalar addition. Scalar addition yields a R0. And is even that what you call R0? I have no idea. Alright, hell yeah, I hit the halfway point, so I think we're going to try to crush, you know what I mean? So, and I'm going to go over the first part of the Gram. See, I'm going to go over this because this was useful to get the first one, but then absolutely not useful to get the second one. Things to pay attention to in this Gram-Schmidt process, you're going to have the perpendicular vectors, that's what we want, and maybe we're going to have our vectors that are at funky angles. That's going to be designated as V1, V2, V3. The first one might be a funky angle that way, but we already said we're just going to make that our first basis. So we're just going to say that funky angle is going to be our first perpendicular. Okay? And then the next one, cool, that's going to be V2. And then, hell yeah. And then we're going to use, that's all we're going to use. I mean, all we know is V1. No, well, yeah, and V1 is going to be that first perpendicular. So even for this proof, we can just kind of, cool, we got that that first perpendicular P1. We want, and then we have this other one, V2, going this way. We want our second perpendicular. So the equation for the second perpendicular is just what we already know, P1, P1, V2, V2, and then P1 again. Cool, all stuff we know. All right, so hell yeah. What they're going to do is they're going to start the process with U, and this is going to be your first V1. You know what I mean? So they're going to say U is your first vector, and then V, this is actually your second vector. And then so, I mean, this process is actually to get this P, which is actually P2. So that is the conundrum, I think, with this process. Because you're going to look at it here and you'll be like, what are you talking about? Well, V1 actually is U. It's just your first vector, and we're just going to choose that. So U is the first perpendicular. And then V is that V2, just the next vector. And then so what we can see is that, let's see if it jives. So we have U as our first perpendicular, P1. And, hell yeah. And this is going to be the second perpendicular. So we have P1 is U, U, U. They just switch the order, and that's a bummer. And that shows you that there is no rhyme or reason. There is no probably right-hand rule. You know what I mean? So it's fascinating. Even on this first one, they actually switch the order of the dot product, but the dot product is commutable. You know what I mean? And I use the word commuting to work, commuting home, you get to the same locations. If something is not commutable, if you multiply one way, you get to maybe an answer. You multiply the other way, you don't get the right answer. But dot product is a commutable property. All right, hell yeah. So there you go. So this is U, 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 and then this is V. They just switched them. But this is that new vector V. And cool. All right, so hell yeah. Let's jive. Alright, booyah. And a lot of this is just trigonometry, so I don't know how much we need to get, you know, how deep we're going to go. But they're going to set it up where they're going to make a vector U. And then we're going to come up here, and then probably just a little bit shorter. Just for picture, you don't have to make it shorter at all. But this is vector V. And then even in the first go-around, they don't even say that you're actually going to use, U is going to be our first perpendicular. For the first proof, they're just going to say, hey, we need to find a perpendicular P. And, cool. And this is where kind of the dot product comes in. But it's a bizarre relationship. Yeah, I can't even explain. That's like the one thing. They're just going to say like, hey, this is the projection of V onto U. And then so in my other video, this is the dot product if you took a unit vector. If you took U hat, which is just U, the vector U divided by the magnitude of vector U. And for magnitude of a vector, you do two parallel, two of them. If you're just doing the magnitude of -2, it's just one. So the magnitude of a number, you just have, one goalpost. This is like double goalposts or whatever. Hell yeah. So if you do take the dot product, V dot U hat, then yes, that is this distance. But so this is the first, because we're going to use dot product. So dot product, just know that it is a multiplication. So if I see dot product of V and U, I am multiplying. So this vector does have a magnitude. We have some magnitude of V, and this has a magnitude of U. Cool. So, if you ever get confused about the dot product, at least friggin' multiply the numbers together. And even do that. Figure out what the magnitude of this one and magnitude is that one. And then and get that number. You'll get a number. Okay. And then just know the same thing for the cross product. Cross product, even though it yields a vector, maybe a vector W, we still have the magnitude of V and the magnitude of U. And if we multiply them together, we might get that number. Now we have this idea that the dot product, if the two vectors are parallel, then you do get to multiply the numbers, and it's just going to be, that value is just going to be the multiplication of the numbers. For the cross product, if the two vectors are perpendicular, what's going to happen is you're going to take the first one crossed with the second one, so using right-hand rule, you're going to get a third vector, but if this and this are perpendicular, that third vector is going to have a magnitude. If you took the magnitude of that vector, is going to be the magnitude of this multiplied by that. So that is something that I'll always reiterate for myself, is that if I'm dealing with the dot product or the cross product, there's still some sort of multiplication. And I think that can get lost just because you're getting values that, you know what I mean? And so let's talk about it. If, when doing the dot product, if these two vectors are parallel, when I multiply the two numbers together, I get 0. But still, you can still think of it as multiplying the numbers together and then taking a percentage based on, if they're parallel, 100%. If they're perpendicular, 0%. And it's kind of based on kind of a circle. So if I go to 45 degrees, cosine 45 is 0.707. That's 70%. So I go 100%. 70%, and then go right to 0. Alright, hell yeah. And then so for this proof, they're gonna give this some sort of length. What they're gonna say is like, well, hey, what if we made this vector? What length would it have? They're gonna say, or what would this vector be? They're gonna say this vector would just be U multiplied by some sort of scalar. So if I have K times U, K could be a positive, it could get bigger. K could be a negative, and it could get smaller, some sort of scalar. So that's what this value is. It's going to be some sort of scalar times U. And I think that's interesting where this value could have just been this vector V dotted with vector U, but the unit vector of it, so divided by the magnitude. And because this is a scalar, it's still just vector V dotted with U, and then you could even bring that scalar out. So maybe we'll look at this, but we're going to do the proof their way. And I had to use like all my skills to even do the proof their way. But even right here, you have a checkpoint, I would say. And so what we're going to do is, cool, we define that. What I'm going to do is, like, what's known and unknown. So what do we know? Well, we know vector u, and we know vector v. So cool. And then the other thing with matrix algebra vectors is still treat it, you know, like, you know, values. You're like, hey, I know this value, I know this value. I also know u right there. And then so what other values do I not know? And then just know that there's still kind of the relationships between these values are equations. So even when you have matrices, you can still have something like this is equal to that. Hell yeah. So what's unknown? So what is unknown is k and p. Okay, hell yeah. So that would be the first step in this process. The second step in this process is, and you know, this is probably because I already, you know, reviewed the proof, but still this is good also, is to ask yourself, can I make, like, if this is what I'm trying to solve, can I get an equation? You know what I mean? Like even right now, could I write an equation for p, for this perpendicular? And for this one, we're going to use the fact that we can use vector, and for this, don't stress out about putting p right here. P is equal to something, something with all of these knowns and unknowns. Just any sort of relationship that combines some of the variables. And so what we have is that we have this vector v is a direction and a magnitude. So we're going to go from here to there. And then so, and we're going to say what vector addition gets us also there. Well, we could go this way and that way. So that's our first equation, is like v is equal to this one and this one. Cool. So that's going to be our equation. V is equal to ku plus p. Hell yeah. And now let's do another double check. So what's known is v and u. What's unknown is k and p. But right now we already did what we wanted to do. Like, it would be cool to write it like this, but we still got a relationship. Now ask yourself, can we write it like this? And hell yeah. And if you can do, you know, this is the first place you can actually, well, hell yeah. Let's just assume we knew everything. That's also a good strategy. And so I'm just going to get p by itself, which is vector v minus ku. Okay, hell yeah. And then in this, like, hey, looks like I only just need to find one thing. If I knew what this k was, I would be good to go. And it's kind of fascinating that I already showed that, like, hey, didn't you say if this was the unit vector, this was just like this length? So we're going to write that on the side, ku. And this is going to be a double check on reality, because that's why this proof was weird doing it in the book, because it was just like, huh, they're taking me down a different route that I don't think I would have saw. You know, I would have done it a different way. But I was appreciative of going down that route, putting my thoughts aside. But we're gonna do this. So ku, what did we say it was? Is going to be this dotted with the unit vector of u. And so we would have v dot u, and then multiplied by the scalar 1 divided by u. And that's not true. Yeah, the magnitude of u. No, that is 100% true. The magnitude of u is this symbol, right? Hell yeah. Alright, hell yeah. So, but now we need to find out what k is. And so here's, you know, and this needs to just be spelled out for the first time. But going into, because this is just the first round, once we add the third direction, you know what I mean, the thought process is still the same. We're going to use dot products. And we're going to know that when we dot one thing into another thing, if the components are perpendicular, this dotted with this, that value is going to be 0. And what we know with vectors is that if I say vector v, Vector v has two components. You know what I mean? So even vector v is going to have a perpendicular component and a parallel component to vector u. You know what I mean? Vector u is going to be the the parallel component. So it's only the parallel component that when you dot them together is going to give you a value. This dotted with that, those components are going to give you 0. So that's the other part of this, is that if we have a vector v, but vector v can be broken up into two vectors, you know what I mean? One in a parallel direction, we'll put a parallel vector sign, and then a perpendicular sign. Then, and we dot it with vector u, which is parallel, then we're gonna use a foiling process. Okay, hell yeah. So let's see if we can do this. And then and that's the other part of this proof, is just like, well, that's not laid out in this first go. Is the fact that we're already saying this is our first parallel vector. So I'm going to put P1 here because that's going to be useful in the other proof. And now I'm going to scratch it out. You know what I mean? Because we're still going to use this proof like they did it in the textbook. And this would be P2. You know what I mean? But I'm going to scratch that out. Hell yeah. Okay, and then this V, this is going to be our V2. You know what I mean? Where this was our V1. And then we call it P1. You know what I mean? Cool. Scratch that out. But this is our V2. Hell yeah. And now scratch that out. Just because I want to use the values that they used. So this is our vector at some funky angle. This is our tugboat being like, nah, I'm going this way, and I want you to go that way. You know what I mean? So go that way. And then we know how to move this ship. So this is the funky one. And we're going to dot it with the one that we've already attributed as perpendicular. And I think that can be hard to start this proof with just a vector going in one direction and saying, hey, this is our first perpendicular vector. I think that's kind of difficult to see. Okay, so let's take our wonky vector and dot it with u. So that's part of this proof, and it'll be part of the next. Because once we get these two, we're going to have a third wonky vector, and then we're going to have to dot it with this one and dot it with that one. And now you're going to see like the equations and the unknowns. Like right now, I just have one unknown. This is an equation. You know what I mean? You could have said this is one equation with two unknowns. I don't know that and I don't know that. But I still have one equation. If I get a second equation, so this is the first equation. If I get a second equation, then I can, and this is going to be in the form of k is, something something v, something something u. And then if I put it in there, hell yeah, then p is just a function of something I already know. Cool. And the dot product can be done v into this perpendicular, that's going to be our one equation, and k is going to be our unknown. So just to kind of spell out that. And then once we're done with this process, we're going to have that third vector that's perpendicular, or just at a wonky angle. And we're going to have to dot it with this direction, and then dot it with this direction. And then we're going to have two values of k, but that's all we're going to need, because we're going to have, our third one is P3, this is P2. P3 is going to be, something something minus K1 minus K2, where everything else is known. So we have checks on everything. The only thing unknown is K1 and K2. So then we're going to take our third wonky vector, dot it into our two now established perpendiculars, and we got two of them, 1, 2, let's say, or 1, 2. And then that's going to give us two equations, because we can, yes, they're two independent dot products. Hell yeah. Okay, so now let's start to crush. So we're going to take V, and we're going to dot it into U. Hell yeah. And then we're going to, oh, and what are we going to say even? Yeah, and that's why this is bizarre. is just because we're just going to take arbitrary v and dot it into u, where I think it would have, it seems like it would have made more sense, I don't know, to actually use a unit vector on u right off the bat, and then that's going to equal ku. I don't want to go down that route, I just want to go down the route that they're saying. But they're going to say that v oh, hell yeah. This is tripping me out, and I think that's a good thing, because this is going to yield a number. Because I'm just like, where's the equation? Like, what is this equal to? Well, we don't know yet. But we are going to say that v is, you know what I mean, this way and that way. V is ku plus p. Alright, so that's what v is. And we're going to dot that with vector u. Cool. And then when we do this process, we can kind of foil this. So we're going to have k, is this, wait, no, this is u. This is, so we have ku dotted with u, and then plus, we have this vector p dotted with u. And so, and then, my bad, because in the book, they're not, we're not going to use this dot product sign ever. You know what I mean? That's what they're, you know, they're going to say this. They're going to do v and then a comma u. So this is the same thing as vector v dotted with u. And you can use this sign if you want to. It's just, it's good to use the funky signs in the book. So again, what's vector v? It's this and that. So it's ku plus p. And now I put my comma, and then what is u? It's just u. So now we're going to kind of do this foiling process. So we're going to say this is equal to ku comma u. So this is the first one. This dotted with that plus this vector p dotted with u. Hell yeah. And then from the matrix proof part, anytime you have a scalar, you can bring it outside of the, you know, the vector or matrix arithmetic. So then we're going to have u dot u, and then we're going to have plus p dotted with u. And from here, because we're saying such, because we're saying this is perpendicular, I know that p and u are perpendicular. So their dot product is 0. So that's what we're going to do here. And then we talked about how if two vectors are in the same direction, then they're parallel. And then literally it's just the multiplication. And they don't talk about that in the book. You know, this whole idea that dot products, cross products, you're still multiplying numbers. It's just a chance that you're going to get 100% or 0%. In this case, we're going to get 100% by multiplying the two magnitudes of u. And so they even skip this step. They go right to this value is going to be equal to the magnitude of u squared. And that's how you're supposed to just kind of memorize it in the book. And I think that's almost from like a memorization perspective, that the dot product of two same vectors is the magnitude of one of the vectors squared, where we can know that the dot product is a multiplication process, and so we can write it as such. There's the magnitude of u multiplied by the magnitude of u. There's no vector or matrix. You can just do this. These are now scalars. So I have parentheses, and I have this. So I have everything's a scalar, and now you can see that this is just k u squared. And now this is the bizarre thing, is because, you know what I mean, constantly I think I have to up my game and just being like, okay, this is, even though the things look funky, there's still properties, you know, and a property, you know, when I say x plus y, I mean, those are kind of property. I don't even know if I'm using the word property right, but they can mean kind of anything as long as, yeah, okay. yeah, I don't want to go down that route. But anyway, so, but yeah, because the hardest thing about this is that we're done. We have our second equation, and if we look at what our knowns are, I know what u is, I know what v is, okay? I know what u is, and then so the only thing I don't know is k. Same thing here. I know, so here is, in this equation, I don't know k and I don't know p. So this is your classic. I have two equations and then two unknowns. So we're just solving for p. And so what we do is we solve this one for k. We say k is the dot product, which they're going to call this the inner product when we're dealing with vectors product. And yeah, so dealing with vectors or matrices both. Don't quote me on that. But for sure vectors, they're calling that the inner product. But vectors and matrices, the dot product can also be called the inner product. I think I looked that one up. Anyway, so we need to get this downstairs. So we got u squared. All right, hell yeah. So we're back. Got a new battery. And booyah. So yeah, we were talking about how like these are values, and we have two equations, two unknowns, and cool. And now we can solve for p, even though it doesn't look, you know, too appetizing. But this is a little buggy. All right, so yeah, this is our equation. So let's at least first start to write that. Minus ku. And then what's k? So we're just going to plug it in. And that's it. You know what I mean? This is our perpendicular vector. It's going to be vector v, our wonky one, minus, what's k? K is just a scalar that's multiplying u to shrink it to here, if this is a visual representation of what's going on. And so, hell yeah, so k is this. It's the inner product, or the dot product, between the wonky one and the one that we wanted, which is a multiplication, but only in the direction we wanted. And we can even take a look at that again. Cool. This scalar is the dot product, but then divided by the magnitude of u squared. So we are going to take a look at that again. And then it's just multiplied by the vector u. So an inner product is a scalar. The magnitude of something is also a scalar. So this checks out. Vector, vector. So we're doing unit, checking units. This is a vector. So this thing must be a scalar. And we already checked it up there. It's a scalar. Okay, hell yeah. So this gives us our first equation. And cool. So now what we're going to do is we're going to, I think we should... well, what did I want to do? I wanted to double check the fact that because we already, you know, I said that if I dotted this wonky vector with u, the unit vector, just a vector that has a length of 1 in the direction of u. That is what a unit vector is. And if I did that, this ku value, the dot product of v with that unit vector. So the dot product of v with that unit vector, which is that vector divided by its magnitude, is ku. Cool. Oh, my bad. And now this is good. It's not even... See, this is a dot product is going to yield a scalar. This is a scalar multiplied by a vector. And so let's say this again. If I take vector v and dot it with the unit vector of u, I'm going to get this length. So if I say this has a value which is equal to just the magnitude, so it's going to be the magnitude of ku. Cool. And then so... let's figure out what this magnitude is. So sorry about that. We have to have a magnitude sign here. And now this equation checks out. We have a scalar over here. This is a dot product. That's a scalar. This is a scalar itself. So cool. And then kind of in this there's a lot of proofs that involve this. If you have a scalar that's part of a vector, you know, I mean, this is something we want to find the magnitude of, you know, we want to find the magnitude of k and the magnitude of u. And so I can just bring this outside. I can say that's just k multiplied by the magnitude of vector u. And the magnitude of vector u is just, you know, I mean, we know what that is. If vector u is like an I hat, j hat thing, it's going to have like sorry, it's going to have xi and then, I don't want to go down that road. Sometimes saying things, I might just say things wrong and lose track. Okay, so we have, yeah, so this is scalar magnitude of u. And now we have the same equation, even though it looks kind of not too cool up here. But we have, hey, there's the dot product. And then what if we get this down or over to the other side? If I get this to the other side, I'm going to have ku squared. If I look at it this way, if I have, okay, I have k on this side and this on the other side. I have the dot product on the other side, and let's get this downstairs. And then so that's the u squared. But the take-home point on this is know your dot products and know that always if you take the dot product of one wonky vector and dot it with the magnitude, well, I don't know what I'm saying now. But anyway, just know that dot products are a multiplication, where if I did v and u, I would have a multiplication of those and a percentage, and that would be the value. Alright, I'm going to leave it at that, but just because this proof talks about the projection of v onto u, and they call this vector ku, I think it also should be known that if you take vector v and dot it with the unit vector of u, you're going to get the magnitude of ku. You know what I mean? And that was a faux pas on my part. I just called this like, hey, a number. But no, this is the vector ku. But it does have a magnitude. Every vector has a magnitude. And so, cool. Alright, so for the next part of the proof, though, we're still going to use like the way that they do it, even though you could kind of backdoor check this way. You know, just kind of another way to look at it. Hell yeah. Alright, let's try to do all three. Okay, so for a picture, I think it's good to, you know, I even need to figure out what kind of picture. If this is the origin, I want to come out to like here. That's going to be there. I'm going to go up. And I'm going to go over. Hell yeah. Sometimes doing a 3D coordinate system and getting something that you want is difficult. Hell yeah. Okay, so what we have is that this, and you can do them long. You know what I mean? You can say that this is vector u. And, you know what I mean? And then this was vector v. But that's it. We're going to stop calling them vector u and v. I'm going to erase these in just a second. And then this was our perpendicular vector. This was vector p. Okay, so now that's enough. Because we're gonna do this in 3D space, and then we can do it in 4D and 5D. And that's the thing. That's the thing that comes up in matrix algebra. That was the first thing that got me, because I'm so used to you know, things being like x, y, z, and then it was just so. This caught me off guard. Is that, like, you know, you would have matrix A multiplied by vector x is equal to solution vector b. But this vector x was going to be x, y, z. And so that's what got me. You know, you could have vector x, and then it's what you were, these were the values that you were used to. You know what I mean, the x, y, z direction. Oh yeah, and let's complete that thought, because then you can just write it like this. Because what if you have x, y, z, w? And then what the hell are you going to write next? You know what I mean? So then you're just going to do this x1, x2, x3. So yes, this, now I understand. This was the first thing that got me. The fact that x1 is what I was associating with x, and then now I had to associate x2 with what I thought was y, and then x3, which, you know what I mean, which I thought was z. But then x4 is going to be w, and then x5 can just be x5, because we're just going to run out of friggin' letters. You know, because you could have this up to xn. You could have it up to x infinity if we get those infinity computers. All right. Cool. So let's start changing these. This is going to be our first vector. And hell yeah. And then this whole process also is we're going to start with V1 is going to be like that. V2 is going to be like that. V3, and that's going to be for today. And then we're going to end it there. We could have V4 though. And then so we're going to give these. Again, we said that they're vectors in 3D space. And then they're all in wonky directions. Cool. So this is V1, V2, V3. The first step is just to be like, cool, we're just going to set that direction now. And you could call this maybe x prime or whatever. But that is going to be our first perpendicular. And so so this now is just V1. This is V2. And then we're going to say that the first one is P1. And so this is the first vector. You know, in this direction. And that's kind of what we're now, you could maybe call this x prime. Because we've oriented our, at least drawing, you know, for that to be the x direction. Or just the x direction. Hell yeah. But now I'm going to cross this out because we're just going to call it our first perpendicular. So V1 is, so we do have our first perpendicular. First perpendicular is V1. And we can write it like this. Our second perpendicular is going to be that equation, and so we can do that, and then we're going to get our third perpendicular, and then I got to call this a video. But the reason I'm able to actually do this, even though, you know, I mean, I might do, it's just my style, we just do what we do, but what's going to help me go through here is doing the unknowns and knowns. What's known, what's unknown, okay? And then, can I get an equation? Can I just make a friggin' equation? Cool. Can I make more equations? And we're going to use the dot product to make more equations. Hell yeah. Alright, so let's start in. So this one is going to be P2. And so let's do it. So if this is P1, this value right here is some sort of scalar 1 times P1. Hell yeah. And because even if we do it like right now, you're just like, oh man, you're losing your mind. Because didn't you call this U? Wasn't this just KU? Well, this just picked up another subscript. And but we're still just doing what we just did before. And then cool. How do we scribe V2? Get an equation for V2. Or first, let's do our unknown. So this is our setup. What do I know? What do I not know? I do know P1. Cool. I do know V2. Okay. And I see, I don't know P2, and I don't know K1. And hell yeah, this is just P1 twice. I see P1 twice on here, and I see V2. Hell yeah, so let's now do our equation. We know that V2, this vector is just this one plus this one. So we have K1, P1 plus P2. Okay, hell yeah. There's our P2. We want to solve for P2. I'm just going to do this in as little space as possible because we've already done this one. We're just using different letters. So P2 is going to be this, V2 minus K1, P1. And then you can kind of just look at what's happening. You know what I mean? Like, well, I don't know. From an equation perspective, I think this is where you need to start. Be like, hey, because even when we pick up our third vector, which is out here. This is going to be our third vector. Still, like how do we get to this third vector? I'm going to go this way, and that way. You know what I mean? So right off the bat, we can get an equation for, and then we're going to have an unknown. You know what I mean? This direction is going to be our P3. You know, so you can kind of pick up on that. So, like even right now, I know what P1 is, I know what V2 is, and I know what this one is as a function of a scalar, and I know how to get to V2. I can go this way and this way. And so right now I can at least get an equation for P2. And I'm going to start the equation just by saying, easiest way to start the equation is just to say, hey, let's take this new vector at the wonky angle, and then stair step to get there, because we're going in a perpendicular route to get there. Alright, hell yeah. Once I get this equation, I can be like, oh hell yeah, there's P2, let's rearrange it, you know, and then I can figure out what do I not know. I don't know K1. And I can say this is equation 1, I just need one more equation. And so that's what we did. Then we did the dot product V2 dotted with, we're going to do V2, comma, the inner product with P1. Oh yeah, and this is where the other is just like, well, why wouldn't you just do the inner product with K1 P1? You know what I mean? Like, let's do that, because I get kind of like, I don't like when it feels like there's only one route to get there. We'll do it this way though, because we're going to do the inner product. We're going to dot this with P1. Hell yeah. And then we're gonna say that this is we're gonna say that V2 is K1 P1 plus P2, and that's going to be dotted with P1. I mean, I should just be writing these bigger. Sorry about that. Okay, so hell yeah. So we're going to do the inner product of V2 and P1, which is way out here. And that's why I don't like this visually, because well, it wouldn't matter if you did this dotted with this. It's still a multiplication where you're going to get a value that's, you know, not visually representative in this space anyway. The only way it's visually represented in the space is if you took V2 dotted with the unit vector of P1. But let's do all three. I think that would be a good place to explore. Then we'll go to P3 and call it a video. Because that's one thing I have to challenge myself. I cannot be in a mood where like I don't want to explore. You know what I mean? It has to be my MO that we're going to do this. Okay, hell yeah. So we're going to say that V2 is K1 P1. Get vector signs on these. Plus P2. And we're going to dot it with P1. So hell yeah. This is that, and we're going to dot it with that. Now we can, and maybe we could do this a little faster. Like it's going to be, well, now let's do it still slow. So use like kind of a foiling method. And this is, what is this called? Just the associative property? I kind of forget, but we're going to do the inner product of this and that. And then we're going to add it to the inner product of that and that. And we already know that these two are perpendicular. So I'm going to say, hey, that's 0 right now. And then I'm just going to say, hey, I'm going to bring out the scalar. And then we're just going to have the inner product of two vectors. And so, you know what I mean? That's going to be the multiplication. Because an inner product is going to give us a scalar. It's going to be the magnitude of P1 and the magnitude of P2. So I will write it this way twice. It's this. It's the magnitude of these two vectors. You know what I mean? So hell yeah. So K1 is P1 squared. Okay, hell yeah. And now we have our relationship. This is V2 P1. You know, so those are equal. And now I'm going to solve for K1. Is going to be the inner product of that wonky vector dotted with our first perpendicular divided by the magnitude of our first perpendicular squared. Hell yeah. And then what was the second way I wanted to solve it? I was asking, well, can't we just take V2 and do the inner product of K1 P1? Hell yeah, let's do that. Okay, so V2 is still K1 P1. And then we're going to plus P2. Let's get vector signs everywhere. So this is our V2. We're going to do the inner product. Yes, I got confused. But yeah, the inner product with K1, P1. Because before we took the inner product of V2 and P1. Hell yeah. And just a foreshadow, this is going to work out because we're going to have, well, it's probably going to work out. We're going to have a K squared. It seems like we're going to have a K squared. I don't know. But anyway, let's check it out. Okay, hell yeah. And then, oh yeah, we're gonna pick up an extra term because, you know, our tight solution for the Gram-Schmidt process is just the wonky vector dotted with the yeah, so it's like if here's my first perpendicular, I'm going to take the wonky vector and dot it with that. Then once I get two perpendiculars, if I have a third perpendicular, I'm going to dot it with this one and that one. Cool. So then, like the way I'm doing it right here, would you would get the same value, you would get the same result, but all these equations would change, and it would have the k in there, which would be just kind of a little bit of a nightmare. But it would still work out. So let's do it. So we're going to use the foiling process, or maybe the associative properties. We're going to say K1, P1, inner product with K1, P1, and then plus inner product of P2 with inner product of P1. So still, P2 and K1, P1 are perpendicular. The inner product or the dot product is 0. And then so you're going to have this. We have two scalars, so I'm going to pull both of those out. And then I'm going to have, you know what I mean, the dot product of two vectors in the same direction. So that's going to be the magnitude of them squared. So that's what you're going to get. That's why you would pick up a K1 squared and then a P1 squared. So then if you solved for K1, well, you would actually have to get this downstairs. You'd have to do a square root, and you would have V2 K1 P1 divided by P1 squared. It would work out mathematically. It would just be, and then you would throw it into your equation, you know, your final equation. So let's do that, because maybe it'll work out. I don't know. And sorry, this is K1. So let's put it into our equation that our perpendicular vector P2 is going to be V2 minus K1. So it's going to be all of that multiplied by P1. So that would be the difference, and that just isn't super tidy. You know, it's going to give you the same answer, but then you're going to have to solve for K1. You would have to solve for K1 every time, and that would be... and yeah, that's interesting, because what's K1? Oh, look at this. It's a loop. Because then if I say K1 is right there, this value would actually... This is a scalar, and it would go in right there. It's like an infinite... I don't even know. I think I just opened up a black hole. So anyway, so obviously we're not going to do that. All right, hell yeah. So let's do the proof for three vectors. So we have our P1. We have our P2. And just know that these P1 and P2s can be any magnitude. I could say that is P2. Let's do that. Do I want to do that? Sure. Yes, because when we solve for P2, we absolutely... Well, no, we solve for that. That was our vector length. That was P2. So it actually does look exactly like that. Oh yeah, so let me think about that one for a sec. Oh yeah. So no, this was P2. So yeah, but V3, there's no chance that it's gonna hit the same, horizontal, y direction as v2. You know what I mean? So we have to actually, so my bad, we actually have to make this more arbitrary. So I'm going to say that it hits, I'm going to say that it's right here. So what if that hits right there? Actually, so this is going to be v3. It's just really hard to draw these so you can pictorially see them. So to get to v3, I'm going to go over in the x direction, up in the y direction, and then over in this direction to get to there. So I would, to box this in, I'm going to be doing this. Okay, hell yeah. And now my picture totally sucks. Yeah, I almost want to... Let's see, can we see that? So this is vector v3. And to get to vector v3, my k1s and k2s change. Because to get to vector v3, this is p1. I'm going to go in the p1 direction. So now this becomes k1, p1. I'm going to go in the p2 direction. We said p2 is right here, so my scalar actually has to be bigger, you know, more than 1. But here, this is my k2, p2. And so that's going to be that vector. So I'm going to go this way, that way. And then this is my new perpendicular. So this right here is going to be just my P3. You know, whatever this value is going to be my perpendicular. And that's where this process, you're not worried about the size of the vectors that you're getting. You know what I mean? Their magnitude. Because you're going to make them unit vectors anyway. Once you know that they are perpendicular, and just the fact that you can get 4 linearly independent, or any number of linearly independent, we're doing 3 today, perpendicular, then you can take their magnitudes, you know, whatever the magnitude of, divide by the magnitude of that, the magnitude of that, you know what I mean, which is the magnitude of v3 is the individual components squared. You know, if there's 3 of them, and then the square root of that. So it's kind of like the Pythagorean theorem in 3 dimensions on steroids, you know what I mean? And it works out. Pythagorean theorem in 4 dimensions, which works out based on that property. Alright, hell yeah. So if I made this video again, I would really hone in onto this picture. But we have K1, P1, and then we have K2, P2, and then we have our perpendicular. So when we do our equation, we're going to say V3 is K1, P1 plus K2, P2 plus P3. And right off the bat, we already have an equation that's P3. We know what P3 is. So our knowns are, we're going to solve for P3. Our knowns are P1, P2. Our unknowns are K1, K2. And if you just treat them like that, hell yeah. You know what I mean? You're just like, hey, we're not doing too bad. And we also know V3. Cool. And we're going to have 2 dot products. We're going to do V3 with the inner product. Think of it as V3 dotted with P1. And again, I'm glad we went over that. It's not going to be V3 dotted with K1, P1, because you're never going to get rid of that term or whatever. It sucks. So we're going to do the inner product of V3 with P1. What do you think this is going to hold? If this is V3, V3 goes in that direction, and this direction. And so what did we say about the dot product? If I dot it with something, it's only the parallel component. And you could also think of it this way. If I have some wonky vector, like only the magnitude, only the horizontal projection in that direction, which V3 we're saying the horizontal projection is K1, P1. So only K1, P1 multiplied by P1 is going to yield a value. And when two, so if I have K1, P1 dotted with P1, it's just the scalar comes out and I get the magnitude of P1 squared, both of those, because it's P1 multiplied by P1. And then you have this scalar. And then when you do the dot product with V2, I have some sort of wonky angle, and then I have V2 here. It's only the horizontal projection, you know what I mean? It's only the component that's in line. So get the component that's in line. The only component that's V3 that's in line with V2 is this K2P2. So we're going to have K2P2 dotted with P2. And then so that's going to be K2 times the magnitude of P2 squared. And then you can kind of see, but then this sucks because this is a rearranging of that. This is once we solve for K, then throw it in. So here is where you can get that kind of that aha. So we're going to do the inner product of V3 and P1. And V3 is going to be K1 P1 plus K2 P2 plus P3. And a big part of this proof is like, aren't these just going to, who cares? Hell yeah, because we're going to do the inner product with P1. That's going to be the first one. And look, these are going to be, I'm not even going to go through. Those are just going to be, if I rewrote it out, those are going to be perpendicular to P1. Because we already said P2 is perpendicular to P1. P3, I mean, we're gaining perpendicular vectors. So we're going to have the inner product of K1, P1, and P1. And this K comes out, and so we have K1 inner product P1, P1. And this is, it's a dot product. So still think dot product of two vectors going in the same direction. I'm going to take their, and a dot product yields a scalar. It's going to be the multiplication of two numbers, 100% of it. So it's going to be magnitude of P1 times the magnitude of P1. So that's where we're going to say this is the magnitude of P1 squared. If you don't see that, and I don't see that on a daily, so it even helps me just to be like, don't skip the step and do it like this. Magnitude of P1 multiplied by the magnitude of P1. Hell yeah. I just throw in the extra parentheses just so you know, I don't know, they're scalars. Cool. Second equation. We're going to take V3 and dot it with P2. And you can see that's going to be K1 P1 plus K2 P2 plus P3. That's going to be V3, and we're going to dot it or do the inner product with P2. But look at this. This is perpendicular. That's perpendicular. Same thing. Scalar comes outside. This dotted with that. And so, hell yeah, it's always good to find those places where you're just like, I know enough, now I can just, you know what I mean, see the answer. Booyah. And then, but we're not done, because in both of these equations, you know what I mean, this is equal to that, and this is equal to that. We got to solve for K1. So K1 is going to be the inner product of V3 P1 divided by the magnitude of P1 squared. K2 is going to be the inner product of V3 P2 divided by P2 squared. Hell yeah. And then we got to throw them into our equation. Our equation is going to be right here. And then we need to rearrange this equation for P3. I should have done that right off the bat. I didn't. Alright, we're just putting together equations, so hopefully my camera holds out and I just want to be done. But hell yeah, so we have P3 is equal to V3, and then let's subtract these both on, you know, get them the hell over there. And then we got minus K2 P2. These are all vectors, those are the scalars. Alright, so now we're going to throw it in. And now we can kind of, this is what I should have done first, because isn't P3 going to look like this? Hell yeah, minus, hey look at that, this is all K1. And does that make sense? K1. Yeah, now I see it. Inner product. And then, you know what I mean? My third wonky angle, my third wonky vector, I'm going to dot it with the first one. And, you know what I mean? Go through that whole process. And, yeah, I mean, it's hard for me to, yeah, because anything that has multiple steps, it's hard, you know, you can kind of see some of the elements, but it's hard to throw them all. But hell yeah, let's put this together. So we have P3 is equal to V3 minus. So here's K1, inner product of V3 with P1 divided by P1 squared minus the inner product of V3 P1. What the hell? Sorry about this. So obviously this was K2 over here, and it was P2 P2. So yep. So K2 was the inner product of V3 and P2. And then it was going to be the magnitude of P2 squared. Hell yeah. And so that should match. So we have P3 is going to be that new wonky vector minus the inner product with the first perpendicular. So we're going to take that wonky and alright, hell yeah. My battery did not make it. But anyway, my camera overheated. But cool. So all we're showing is that these two things are the same. And this value was that wonky vector dotted with that first perpendicular. This is the new wonky vector dotted with the second perpendicular. And hell yeah. And so, and then you can just add more. So what would be the strategy to add, a fourth direction? I would think of it like this. I would say, first you're going to do V4. So we're going to say V4 is one way, and then perpendicular another way, and then perpendicular another way, and then perpendicular a fourth way. So this is going to be V4. And we traveled in 4 different ways. When I dot this V4 so we're going to say that this way, was our first perpendicular. This way was our second perpendicular. Oh, yeah, I was wondering if I thought that was a brand new pen, and I was super bummed. I was just like, because pens are getting expensive. Holy hell. But no, that's just a used pen. Let's use this one. Okay, so we're going in the first direction of the first perpendicular, then the second perpendicular, and then the third perpendicular that we found. Now we're going to go in the direction of the fourth perpendicular. That's the one we don't know. So the process is the same, that we can get our equation. And do you think we can get our equation is going to be V4 is going to be, we went this direction, only a K1 P1. Only some sort of scalar of this P1. Then we went K2 P2 this direction, and then we went K3 P3 that direction, and then we went P4. So we can say that V4 is equal to this, and that. And so if V4 is equal to all those things plus P4, then I'm going to say P4 is going to be V4 minus K1 P1 minus K2 P2 minus K3 P3. And then I solve for K1. And then so we just need an equation that relates. So if I take the dot product or the inner product of this onto K1, what I have here is, back it up. If I take the dot product of V4 with P1, then I'm just getting the horizontal projection. This is the perpendicular distance down to K1. And so that's kind of what I didn't show from... I drew another diagram because I'm thinking about doing this one again. Is that... so here's V2 dotted with P1. And I did this in the first video. Where if I have... So if here's P1 and here is V2... the dot product, I think a very important part of this was, because I made it a preliminary video on this, but I think, if this is your first vector, and we're calling it our first perpendicular, and then we have our second vector that is some sort of wonky angle to it, the most important aspect of this is to do a perpendicular to this vector, and then, do a line of action on that, and then extend this vector, in the R1 space, and then do little perpendiculars just kind of wherever, and then move these perpendiculars until your captured this vector v2 and then draw little street lights, and then the horizontal projection will be, you know what I mean, this will be an actual, well, it'll be a vector, but that horizontal projection now is what you're calling K1, P1. Because it's in the same line as this perpendicular, and it's just a scalar multiple of it. But I guess, yeah, I really honestly like to do the fact that you can do this as a dot product. I think that is the most sane thing to do in this proof, honestly, is to go v2 dotted with a unit vector p1. So we would do p1 divided by p1. Because if you do that, I don't know, it seems like, does the k term not show up or something? Oh, yeah, no, the k term shows up, but it's going to be the absolute value of that. So this distance right here, because I like to think of that. I like to be like, well, if here is the actual vector, and if I dot product with the unit vector, I'm actually getting this length. So that's going to be the absolute value of K1, P1. And so mentally, I don't know, that seems to make more sense than this idea of just being like, well, we're going to do the inner product of V3 with the P1 direction, and V3 has these components. We're going to go K1, P1, and then we're going to go this direction, which is P3. Yeah, so I didn't show that on here. This is P3. And then I'm going to go up K2, P2. That's how I'm going to get to this value. You know what I mean? And, or I could go this direction. I could go K1, P1, and then I could say this is K2, P2, and then I could go over P3. But yeah, it all jives. And so if you have four directions, then, you know what I mean, when you take your inner product of V4 and P1, only the term, because this V4 is going to be all these terms to get to V4, but only the K1, P1 is going to be an inner product with P1, and you're just left with K1, P1 squared. So that's going to be that term. So that's going to be the K1 term every time. The K2 term is going to be the same thing. V4 inner product with P2. And then so V4 is all four of those, but only the K2, P2, and P2 term generate. And so you're going to have K2, P2 squared. Hell yes, that's going to, and then obviously if you solve for K1, it's going to be that inner product divided by P1. And so that's essentially, that's it. That's going to be the Gram-Schmidt for P4. So you're going to, so for this K1 term, it's going to be V4 P1 divided by P1 squared. So, and then the K2 term, wonky vector, P2 divided by the P2, anyway, it's just this K2 term. So there you go. Or the K2 term is this, and it's going to be the inner product divided by the magnitude. Alright, hell yeah, that's going to be a video, but I'm going to try to do this, and I'm going to try to walk through it in kind of that 5-minute progression. I'm just not skilled at that. So that'd be kind of an interesting thing to put at the end of this video. I'm going to do an introduction, but we're going to be done with this, so thanks for joining me. Booyah! Alright, hell yeah. So we're going to do some linear algebra. We're going to do the Gram-Schmidt process. And we're going to do this equation right here. So the first one is just straightforward. The second one, kind of tricky. And then the third one, hell yeah. Okay, and so the first one's kind of going to look like a triangle like this. And booyah, I started this video and almost struck out, but I found out something new. Because what we're going to start out with, if we're going to do the 3 vectors, and what we're trying to do is we have 3 vectors and they're just all wonky. You know what I mean? But they are linearly independent. Like none of these vectors are in the same direction. You know what I mean? That's one way to look at it. Hell yeah. And in 2D space, we talked about how if I have two vectors, you know what I mean? This is how we walk across the Earth. I'm going to go this way and that way. And if these are my two vectors, I can go anywhere. But, you know, let's say you walked, you know what I mean? Let's say you walked like this, you know, like that. You, like, took a step this way and then took a step that way. You could still go anywhere on Earth because you can walk back this way and maybe you can do this way. Those are linearly independent. It's just, it would be nice if we could do this. It could be like, hey, if I want to go over there, it's like, hell yeah. Okay, so keep in mind that these are 3. So this is going to be my V1. This is going to be my V2, and this is going to be my V3. They're all wonky angles. The first thing we do is we set our first one equal. Our first one is going to be our perpendicular. And so that's kind of interesting, you know. And so you might as well call this maybe the x-axis. Now, what happens is just like, well, couldn't I draw a perpendicular line here? And that's where I got hung up. And like, couldn't I draw a perpendicular line here? Sure. But if you have two vectors, you know, like let's say it's an array in space, you can only put a flat sheet of paper. You know, if this is a note card, and here's my two vectors. I'm going to be fumbling. You know what I mean? There you go. If those are where the vectors are facing, that's going to be plane. You know, that's going to be plane. But if you say that these are your two vectors, this has to be planar. And so, booyah. So if I do draw a perpendicular line, so if these are the two vectors, the note card is going to be placed right on there. It just happens that I drew the first two vectors, so they are actually taking up this xy space. So this is y, this is the x direction. Hell yeah. But this third one is not in the z-axis. It's wonky. And so that's going to be part of our deal, is we're going to have to find a perpendicular. Hell yeah. And can we do this? We can probably do it in 10 minutes. So for the first one, you're going to say, hey, this is V2. Well, what are we going to do? Well, we just defined that this was perpendicular, and then so we're going to define this as a vector. That's going to be P2. Then we're going to say, well, I know P1, and so let's box this in. We know that vectors, you know, follow the visual properties of triangles, and if I know this is P1 out to this point, I can just say, hey, this vector right here is just some sort of scalar of V1, and I'm going to call it K1. And now we're ready to bust it out, because I can say V2 is just K1 P1 plus P2. And this is the first aha moment where you're just like, what are we trying to find? We're trying to find this. Well, rearrange it for that. So this is P2 is V2, and then subtract K1 P1. Hell yeah. So now we're going to jump ahead, because when we do find P3, so let's say we found this. You know what I mean? We actually know everything. Okay, now we're going to jump to now I have a third wonky vector, and what I'm trying to find is and I know my first two. My first perpendicular is there. That's P1. My second perpendicular is here. And these are transmissible. It doesn't matter if I put P2 there or if I put P2 there. Those are the same. It doesn't matter if I put P2 right here, which we do in a second. Okay, hell, I just know them after solving for that first go. And then for the second go, I have another wonky vector. That's V3. And then so I'm going to do that same process, because I'm finding perpendicular vectors. There's the first one, there's the second one. And like we said, I'm trying to get to over here by going this way and then that way. So let's go to V3 using at least what we know. So I'm going to go to V3 going along our first perpendicular. Hell yeah, I'm going to go that far. And then I'm going to go along, our second perpendicular. And then I drew this, so I actually have to go farther than P2. P2 is just right there. I have to go all the way up to there. So there's going to be our little difference. And then I need to go in a perpendicular direction. So here is the plane, and perpendicular, if I'm saying this plane is the board, perpendicular to that is out of the board. And so in XY space, we just draw that, have to draw it at some sort of angle so you can kind of see the vantage points. But hell yeah, so this is that direction. And so now I can say this is P3. And so I could say that's P3, but I also drew it in two different ways. I could go this way, I could go this way and then say this is P3, and then go up in P2. Hell yeah. And it's really good for this proof to be like, hey, draw your first P1 way out here, because we had to use a K1 P1 for our first go. So for our second go, we're going to get rid of that. For our second go, you know what I mean, we're only going to go this far in P1. So this is a new K1 P1. And then I'm going to go, this far in P2. So this is going to be K2 P2. I have it drawn over here. But you can easily see the difference between what P2 is. And K2 is going to be a scalar multiple of P2. Hell yeah, we got 3 minutes. Alright, booyah. So then we have P3. So we're going to say V3, to actually get there, is a stair step, is going to be K1 P1 plus K2 P2 plus P3. And at least right here, you can be like, aha, there's P3. So we're going to write P3 is V3 minus K1 P1 minus K2 P2. So we have our equation, we just don't know what K1 or K2 is. But we do use the dot product. And I only have 3 minutes, so we're just going to go for it. We're going to take the dot product of V3, and we're going to dot it with this P1. So we're going to do the dot product, V3, P1. We write it like this. You might be more familiar with it like that. But what happens is we're going to say V3 is actually K1 P1 plus K2 P2 plus plus P3. And then we're going to dot it with P1. Hell yeah. And then this could be also, you know what I mean? And we can FOIL this through. So if you're more familiar with it like this, K1 P1 dotted with P1, you know what I mean? K2 P2 dotted with P1. And then P3 dotted with P1. Well, what happens is we already said P1's perpendicular, P2's perpendicular, and this V3, when we dot it with, and we're saying that V3 is K1 P1, K2 P2, and this new perpendicular. That if I'm dotting it with P1, only these two will actually generate a value. These will generate 0. Two vectors that are perpendicular will be 0. So then we have this inner product, V3 P1, is equal to K1, and then we have the dot product of two vectors, which is just their magnitudes squared, because you get 100% of them, so it's just the magnitude squared, and then we solve for K1. K1 is V3 P1 divided by the inner product. Alright, hell yeah. And that's, we got 48 seconds. And then we would do the same thing. We would dot V3 into V2. And so you do the inner product of V3 into P2. And so this is V3. And then if I throw a 2 here, only these two are going to generate. And we got K2 and then the inner product P2. Hell yeah. And we got 20 seconds. So I didn't do it in 10. Maybe we'll try again. But then you're going to throw those values into this equation for K1 and K2. And that's going to be your answer. And then so in 9 seconds, here it is. This value is K1. This is K2. And again, hell yeah.